There are warm-up problems up there. Don't try the 4x4 matrix until after you've done number 2. So once you do the 3x3 on number 1, then go down to number 2, and then try number 3. Do that 4x4. Thanks. Does anyone have any noteworthy news from since the last time we met? Guess not. I must have enthralling warm-up problems. Yeah. All right, who'd like to start us off with a prayer? Anyone? Go ahead, Braden, thanks. Amen. Thank you very much, Braden. Wonderful prayer. Let's take a few comments about devotional. How was devotional? Did someone that watched it want to tell us with the rest of us about what it was about? here and then there?
She talked about how science and faith can work together rather than being a hindrance to each other. And she kind of like disproved the theory that a lot of scientists have that God can't be real because science exists.
Great. Nice. Do you want to add anything?
Yeah, I really enjoyed it. And I like that she talked about how science is agnostic. How like science, as much as science can't prove that there is a God, science also can't prove that there's not a God.
Right. And there are scientists that will use science to say that there is not a God. That's a philosophical view and not a scientific view. Scientism rather than scientific. Great. I always thought it was funny when you'd hear, I've heard scientists say like, there's no God because science, we know science can explain all this other stuff. And I'm like, scientists can't even explain how snakes move completely. I mean, like, and you have the audacity to say that you can't, that there is no God. I'm like, wow. But one of the things she brought up, she said, don't let your God be a God of gaps, which I thought was wonderful. She said a lot of people start putting God to explain things that we don't have explanations for, but then science eventually comes and explains those things, and you don't want your faith to be based off of that, right? My faith in God isn't dependent upon whether scientists know how snakes move or not. So when they show that snakes move, I'm not going to lose my testimony or anything. She explained the God of the gaps thing much better than I did, but I'd strongly encourage you to get on and listen to it. We have. There's something else I was going to say about devotional. Yeah, I strongly encourage you to get on. It was wonderful, very, very good. I missed a few minutes, but the stuff that I saw was really nice. Okay, so take a few minutes and work on these problems. And be prepared. I'm going to ask you if you have any questions from the reading or videos or these problems or anything. So in a few minutes, so be prepared for your questions. And for those of you that came in late, don't do the 4x4 until after you've tried number 2. So do the 3x3 for number 1, then go to number 2, and then if you finish that, or if you're stuck there, go to that 4x4. Okay. So quickly, I emailed out the survey. I haven't checked today to see how many people have filled it out, but I saw about 30 have had yesterday. So please fill that out. And then on an upcoming Learning Suite, you'll be able to, we'll give you an extra credit problem and you can, on your honor, report that you completed the survey. And I'll have the TAs help me go through all that. We have an exam coming up. I think it's the end of next week. Thursday will be 4.4. That'll be the last section on this, on what's covered in this next exam. Then I think we review on next Tuesday, and then we have the exam next week. So that's coming up. There are already review materials up online. More tests this time. I think there's 3 or 4 with keys, so you can start reviewing those. This tends to be a harder test because, as you can see, like just the concepts are more difficult. Some of the computation stuff is a little more intense. We're also putting the slides from class, we're also putting them up on Learning Suite so you can have access to those. And homework, I have the homework up over here. So you're doing the pre-stuff for 4.4, and then you have the written homework on 4.3. Just this morning, I did delete one of the problems on 4.3, the written homework. So I apologize if you worked way ahead and you did extra work. I'm sorry. One thing I wanted to show you is, so some of the questions that I got in office hours over the last few days, there are things where Wolfram Alpha could help. Like if you're having trouble, like with the finding solutions of equations or finding the eigenvalues and eigenvectors, because it's very algebraic intensive and you miss a sign and then things don't work out well. So this is where technology can help you out quite a bit. So if you go to Wolfram Alpha, then you can type in make this bigger. You can type in a matrix, and the way you do that is you start with the curly brackets and end with the curly brackets, and then each row, it goes by rows, you separate, you also put those in curly brackets. So this is 6 comma -7 and 0, 3. So that's the notation, and if you want to know what the eigenvalues are or eigenvectors or determinant, you can just write determinant of and then put that in there. But also, if you just put in a matrix, it tells you all those things anyway. So the determinant of this is 18. There's the inverse. Here's the characteristic polynomial, which you guys just learned about. Here's the eigenvalues. Here's the eigenvectors. Here's how it's diagonalized, which will be the next section that we cover in 4.4. So all the stuff we're learning, it knows that these are the standard things that you should know about a matrix, or that people are searching for a matrix. The trace, by the way, is another number like the determinant, and it is just the sum of the entries of the diagonal. So 6, if you add the 6 and the 3, you get 9, that's the trace. Easier to compute than the determinant, but not as important. So, so if you're struggling to get an eigenvalue on WebAssign or the right eigenvector, come and put it in here and you can start to see where you might go wrong. Like, oh, I didn't get the right characteristic polynomial. I had lambda squared minus 10 lambda. Oh, and that's why I can't solve it. It's not, things aren't working out. So then you can go back and do that. Okay? Can help you with problem solving, and you don't get bogged down in those little things. Okay. And before we dive into the problems on the warm-up slides, questions on anything that you read or videos? Anything from the videos? Yes, Braden? Okay. All right, we'll talk about, I'll hit those today. So that question, for those of you online, what's the different, what is algebraic and geometric multiplicity. And with the true nature of the book, the author throws them out there and doesn't tell you why they're important at all. But they are, and that will come up next time. So, okay. Might even get to it today. Other questions? Or things that were confusing? Yes?
You go into more depth on the way that you can express a matrix to a power and then easily calculate that with the...
Yes. In fact, that's number 2 up there. That's what we're going to do with number 2. So easy computation of a to the n, or a to the n, or a to the n times b, or something like that. Okay, yeah, that's exactly what the second one's going to help us get at. So good. Other questions? Okay, if you have some, holler. So to build up to these, let's start. I'm just going to start working through this 3 by 3 one here. So I put down the matrix, I subtracted my lambdas, and luckily I've got you to check all of my work. I started to do the determinant. I just did my 3 this way, subtract my 3 this way, and I got this far. Does anyone see any mistakes yet? This is a super practice in combining like terms. Oh, you did find a mistake. Over here, so I multiplied, so I had these 3 terms that were right down the diagonal, and I multiplied them together. So I squared, I multiplied these 2 first. So 1 times a minus 1 is minus 1. A minus 1 times a minus lambda was a positive lambda. 1 times a minus lambda was a negative lambda, so those added to 0. And then I got a negative lambda times a negative lambda was a positive lambda squared. And then I multiplied all of that by 1 minus lambda. Did I do it right? Maybe not. 1 times a minus 1 got me my minus 1. 1 times lambda squared was a positive lambda squared, right? Okay. My lambdas look too much like negative 1s. So that should be positive. So because it's 1 of all of that, and then I subtract the negatives, I get a positive lambda squared, right? So I get a positive lambda squared. I'm sorry, I get a positive lambda. So I didn't get that in there. Positive lambda, and I get a negative lambda cubed. Okay? So that's where I got that mistake from. Thanks. So let me put in my lambda, and we'll get it fixed over here. So this is a positive lambda, and I need to add a lambda. Okay, so now let's combine all of our like terms. I got a minus lambda cubed, then my lambda squared, so I have a lambda, is that my only lambda squared? So plus a lambda squared. And then what about my lambdas? I have a positive lambda, a minus 2 lambdas. So those add to 0. Is that what you guys got? Okay, some of you got that. So we'll be wrong together. And then I have a minus 1 and a minus 1 and a positive 2. And so that adds to 0. So you just end up with this. Is that what you guys got? Nice. Okay, good. So this is our characteristic polynomial for this matrix. Okay. If we write down, so we're going to use that to write down a minus lambda cubed plus lambda squared equals 0. We're going to solve. This is called our characteristic equation. Okay, those are the differences. The characteristic polynomial turns out to be, it's important for us because we need to solve it. You know, we're going to use it to set this up and solve for our eigenvalues. It also has importance in more theoretical parts of linear algebra. So here we can solve, we can pull out a lambda squared. We get 1 minus lambda equals 0. So lambda equals 0 and lambda equals 1. So you guys got? Okay. So we have a cubic here. We have a third degree polynomial. There has to be 3 solutions. Okay? There's got to be 3 solutions, but I only wrote down 2. What's my problem? 0 is a solution twice. It's a repeated solution. Okay? And this is where the algebraic multiplicity comes in. So 0 is an eigenvalue with algebraic multiplicity 2, and lambda equals 1 is a solution with algebraic multiplicity, I'm not a solution, is an eigenvalue with algebraic multiplicity 1. This means that algebraic multiplicity is just how many times they're a solution to the characteristic equation, or how many times they're a root to the characteristic polynomial. So that's the algebraic multiplicity. Good with that, Braden? Okay, other questions on the algebraic multiplicity piece? This tends to be the easier one. Okay. So let's go ahead and find the eigenvectors associated with these. So let's come back here, subtract 0 off the diagonal. So we just get our regular matrix, -1, -1, 1, 0, 1, 1. I recorded that correctly, right? I hope. Okay, let's row reduce. Let's add this row to this row. 1, 2, 0. So we get a 0, we get a 1, we get a 1. And look, we've already seen we've got an issue here. So we're going to add a -1 this row to this row, and we get zeros. I can get rid of this right there, the 2, by multiplying by a -2 and adding. And if I do that, that becomes 0, and this becomes a -2. We good? Is that what you guys got? Okay. So now how are we going to use that? Well, we're going to try and find the null space of this matrix after subtracting 0 off the diagonal, which of course is the null space of the original matrix, because we didn't change anything by subtracting 0 off the diagonal. Let me just write it up here so it's not as bad. So the null space is where these equal the solutions of the system, the homogeneous system, where we have the zeros over here. So I'm going to write this down in terms of x1, x2, and x3. I have a free variable here with x3, right? There's no pivot columns. I have these 2 pivot columns. This x3 is not a pivot column. So I can write this down as x1 minus 2x3 equals 0, and x2 plus x3 equals 0, and x3 equals x3, because it's a free variable. So now I can pull all the x3s over to the other side in those first 2 equations. What do I get? x1 equals 2x3, x2 equals x3, negative x3, x3 equals x3. So now I can rewrite that system, or sorry, these solutions, infinitely many solutions, any vector, x1, x2, and x3 of the form, I'm going to replace this x3 with t on the right-hand side, t2 minus 1, 1. So we'll be in the null space there. So any multiple of that. So this is, an eigenvector. Oops, can't spell eigen. So we'll call it E vector. This is an E vector for lambda equals 0. And a basis for that eigenspace, which is the null space of the matrix once you subtract the eigenvalue off the diagonal. The basis for that eigenspace is that matrix, or any scalar, non-zero scalar multiple of that matrix. Okay? Yes, Peter? Is it Peter?
Yes.
Okay, go ahead.
Is it typical to use x1, x2, x3 when doing this kind of a problem?
The problem is once you get to 4 by 4, what do you use after z? So I'm comfortable using x, y's, and z's. That's what I like to use. But when we start doing 4 by 4s and 5 by 5s, I did this to help you guys get more comfortable with it, the subscripts. So it's easier to generalize those more. It's more like what you're going to see in the proofs and arguments and explanations that the book does. So you could do it either way. Because whatever you call it, the first one's going to be 2, the second one's going to be a -1, the third one's going to be 1, right? They're going to happen in those ratios. So you don't have to call it, yeah, whatever you call it, you're going to get the same thing. Good question. Other questions? Peter?
Is that how we should write down what our eigenvectors are? Just something simple, like there's no standard notation for writing.
Yeah, if it asks for the eigenvector, you can just write out the vector. If it asks for the basis for the eigenspace, then you put it in a set, like the set notation to say, hey, this is a set that I'm thinking of, like the whole span of this thing. So, yeah. So if it just asks for an eigenvector, then you don't have to put the brackets around. But it asks for the basis for the eigenspace, then put it in curly brackets. So you're saying, hey, this is the set of stuff that makes up the eigenspace, the span of which makes up the eigenspace. All right, so we have one eigenvector. And so we have a one-dimensional eigenspace associated with lambda equals 0. That is the meaning of the geometric multiplicity. So we just have a line that's the eigenspace associated with lambda equals 0. So it's one-dimensional. So the geometric multiplicity of lambda equals 0 is 1. It's one dimension. We had 2 with algebraic multiplicity. But when we went through and found the dimension of the null space associated with that, we only got a one-dimensional null space. So the geometric multiplicity associated with lambda equals 0 is 1. So they can be different. The geometric multiplicity, though, cannot ever be larger than the algebraic multiplicity. That'll never happen. So, Sophie?
So what would a geometric multiplicity of 2 look like? Would it be like a matrix, like a 3 by 2 matrix? Or?
Good question. That question was, what does a geometric multiplicity of 2 look like? So suppose we subtracted a lambda. Suppose we subtracted an eigenvalue and row reduced, and we got this. Okay. Suppose we got this when we row reduced after subtracting an eigenvalue off of the diagonal. So we didn't, in our particular case, we ended up with this. But if we ended up with something like this, we have 2 free variables. It's supposed to be a 0, not a kidney bean. Okay. Then we have 2 free variables here. And when we finish writing out what the null space is, we're going to end up with 2 vectors. We'll need 2 vectors to talk about the basis. Because we'll have like x1 equals a minus 2x2 minus 3x3, but x2 equals x2 and x3 equals x3. So you're going to have a vector here, minus 2, 1, 0. That'll be one vector associated with this one. and you'll have another vector minus 3, 0, 1 associated with that one. So we have two eigenvectors if associated with that lambda. So the basis, we'd have to write down both of those in there. Say this is a basis for the eigenspace. Okay, does that help? Thank you. Other questions? Okay, so geometric multiplicity can never be larger than algebraic multiplicity. Usually they're the same, but they don't have to be. It's nice if they're the same, and maybe by the end of class we'll be able to figure out why they're nice. Okay, have we finished this problem? Oh, we didn't. If we would need to subtract 1 and keep on going, right? But yes?
Just a random question. Can the eigenvector ever be a zero vector?
The eigenvector is a non-zero vector. So 0, 0, 0 is never an eigenvector. It'll be in the eigenspace because 0, 0, 0 is always a solution if you've got zeros on the other side. So, but eigenvectors are considered non-zero vectors. So, great. Yes.
So I was just double checking. My eigenvector can be different from yours, right? Like in theory. So like when I did the problem, I used x1 and x3 as pivots. So I found that was easier to reduce. So my x2 is 1. Is that okay or not?
So it is true that they can look different, but they should be scaled. Did you just get a different multiple of this?
Yeah. No. So I was just curious if that's all we can use whichever.
That's right. Any scalar multiple of this vector is an eigenvector too. So we can multiply it by 5. You can multiply it by, well, as long as it's not 0. But yeah, great. So that question for those online was, can my eigenvector look different than your eigenvector? Yes, but they will be scalar multiples. In this case, you might get something where the span is the same. They might look both be different. Actually, I'm not so sure. I'll have to think about that one more. Okay. I'm not gonna go and do 1 here, like subtract 1 off the diagonal and then do the same thing. Hopefully you've had enough practice with that. So, what's the next question? Okay. All right, so here's this problem we worked on before when we just started with eigenvalues. I had that GeoGebra thing that showed the population of the rabbits and the foxes. And one of the questions you'd like to know is what's going to happen with the populations? Like these are things that people that do biology, they do all the time. They've got these models for populations. And it can help them know where to focus their efforts on preserving different species in different chains. So here we have 1.5, a -1, 1.1, and 0. And the question is, if I start with a population of 1, 2, which I think I said rabbits was in thousands and ferrets was in 100. So this is 1,000 rabbits and 200 ferrets. So it's not 1 rabbit and 2 ferrets. Okay. You can't get more rabbits if you've only got 1 rabbit. So we want to know what, oh, flip. Did I say 7 years?
Wait, is it -0.1 or
This is -1. That's -0.1. No, -1.
15 years?
Is it -1? Yeah, 0.1. -0.1. Okay. Okay, negative 0.1 and 15 years. So 15 up there. We want to find out that. Now, you can, this isn't too bad. I mean, you could multiply this matrix by itself 15 times if you wanted to. If you had a 3 by 3 or a 4 by 4, or you easily get situations like this, we've got a 10 by 10. It's not something you want to do by hand. This is a big problem, is to figure out how to do in systems, how to reduce the computational complexity. So the book shows you a way to do this. The key is, if we can rewrite this vector as a combination of eigenvectors, then this is really nice. Because then multiplying this by an eigenvector is the same as just a scalar multiple times that vector, and we can easily raise that to a power. So the first thing we need to do is find the eigenvalues and eigenvectors of these. What are the eigenvalues? You should be able to tell me right away if you picked up the important theorem from the book. Yes. 1.5 and 1.1, why? Yep, the eigenvalues of a triangular matrix are the entries of the diagonal. So in this case, you can see it because if you subtract off 1.5 in both cases, you're going to get a zero column. And if you subtract 1.1, you're going to get a 0 row. Either way, those are the two ways you can get a non-invertible matrix, by subtracting something along the diagonal. So we can, so for lambda equals 1.5, 1.5 minus 1.5 minus 0.1, 0, 1.1 minus 1.5. So I'm subtracting off the one eigenvalue, seeing what the solutions are for the homogeneous equation. I get 0, 0. I get a minus 1. Down here, I get a negative 0.4. I get a negative 0.1, sorry. 0, 0. And so this, I can make this is going to be my pivot position. So I can make that 1 by multiplying by a negative 10. Oops. Can't write one thing and say another. And then I can use this to make that 0. Multiply by 0.4 and add, that goes to 0. So I end up with this. So what does that solution mean? That means x1 here is a free variable. So, and x2 is not. So I can write x1 equals x1 and x2 equals 0. Okay, so x2 equals 0, x1 equals x1. So that means that 1, 0 is the eigenvector associated with lambda equals 1.5. Okay. All right, questions on that so far? Okay. All right. We haven't had many where you end up with the first row as zeros, right, where this isn't a pivot position. But if you write out the system, this says x2 equals 0. This we don't have, this is nothing, and we have a free variable, so x1 just equals x1. And then that's what you end up with. And you go from there. Okay, what about lambda equals? What about lambda equals 1.1? Then you subtract 1.1 off the diagonal, negative 0.1, and 1.1 minus 1.1. Okay, and we end up here with 0.4, end up with zeros on the bottom row, 0 over there. Here we end up with a negative 0.1, and here I can multiply by 10 fourths, or to get that to be 1 or divide by 0.4. And what do I end up with? I end up with 1, 0. This one, if I have 0.1 and I divide by 0.4, then I get just a minus 1/4. 0, 0, 0. And so this, here my x2 is a free variable, and 1. What do I have here? I get x1 equals, for this to equal 0, x1 has to equal 1/4 x2. So x1 equals 1/4 x2, and x2 equals x2. So then so for lambda equals, let me put it down here. For lambda equals 1.1, the eigenvector is 1/4, 1. Okay, is that what you guys got? Is that what you guys would have got if you did it? All right, so why are we doing all this? Because we're trying to figure out what this to the 15th is. And the strategy we're going to use is to rewrite this 1, 2 as linear combinations of these eigenvectors, this and that. So the question is, how much of, I'll just write A times 1/4 1 plus B times, so 1, 0, 0, 1, 1, 0 equals 1 equals 1, 2. Well, this is just a system of equations, or you can write it as a matrix equation, you can row reduce, we can do all that. But this is actually so easy, you actually don't even need to do that. Because there's only one way for me to get this 2, and that is I have to multiply that 1 by 2. So it saves us a little work here. So A has to equal 2, and that means that 2 times this 1/4 is going to be a half, and a half plus B has to equal 1. So 1/2 plus B equals 1. So what does B have to equal? B is a half. Did I do that right? I hope so. When I did it before, somehow I came up with a negative, but maybe I made a mistake earlier. I had to minus 1/2, but okay, we'll try it. So A is 2, so 2 of these and a half of this is the same as this vector. Okay, so how's that going to help us out? That's going to help us out tons. Now we can do a little algebra and rewrite things, and then use the fact that those those are eigenvectors. So 1.5, negative 0.1, 0, 1.1, that times 1, 2 is the same as, to the 15th, is the same as 1.5, negative 0.1, 0, 1.1 times, you can do parentheses with this, 2 of 1/4 ones plus a half of 1, 0, okay, to the 15th. Good with me so far? Okay. So we basically wrote, this was in the standard basis. This is rabbits and foxes, rabbits and ferrets. Foxes. What was it, foxes? I think it was saying ferrets before. Rabbits and foxes. We've actually changed the coordinates. So we're no longer using rabbits and foxes. We're using we're using coordinates in a different basis. And you might think, why do you want to change? It's so straightforward, rabbits and foxes. But this makes it so computationally, it's really, really nice. So that's going to be the same as, I can pull this 2 out in front, and I'm going to distribute this matrix to the 15th power over. That's going to be 2 times 1.5 minus 0.1, 0, 1.1. Here the book would just call this A or something and then do it. He just does it in general. 1/4, 1 plus 1/2, 1.5 minus 0.1, 0, 1.1 times 1, 0. On the surface, that looks more complicated than what we were trying to do. Doesn't that look simpler than all of this? It does look simpler, but it's not. Why not? What's the kicker here? Andrew? Yeah, this is an eigenvector for this matrix. So multiplying this matrix times this eigenvector is the same as doing what? Yeah, multiplying it by an eigenvalue, and that eigenvector is associated with an eigenvalue of 1.1. So I can replace this matrix multiplication with just 1.1 to the 15th. Every time I multiply it by this, it's the same as just multiplying that by 1.1. Yes, in the back. Oh, nice. Good question. So we have something like this, right? Or so this is a 2 by 2, and this is a 2 by 1. So when we do that first multiplication here, if we choose to do it this way, we still end up with a 2 by 1. So we'll still end up with a 2 by 1 matrix, and then a 2 by 2 times a 2 by 1 will end up with another 2 by 1. And so we will always just end up, if we do the multiplications kind of from this end, we'll always have a 2 by 1 times a 2 by 2. Till the very end, we'll just have a 2 by 1. Yes. So is each one of these an eigen? What if after I do the first multiplication, how do I know it's an eigenvector? It's because this multiplication is going to be the same as a scalar multiplication. So I'm still on the same line. I'm still on the span of that, right? So it still applies. Very nice. Yeah. Thanks for bringing that up. So every time we multiply this, it's just the same as taking 1.1 times that vector, which is just the same using our rules of scalars. We just get 1.1 to the 15th times, 1/4, 1 plus 1/2. And how about this? This matrix times 1, 0, that's the same as multiplying it by 1.5. That's the eigenvalue associated with this eigenvector. So this is just the same as doing 1.5 to the 15th times 1, 0. And then you can write this out as one matrix if you want. So 2 times 1.1 to the 15th times a 4th plus a 1/2. So this is my upper value. So I have 2 times this times the upper value plus a 1/2 times this times 1. That's my upper value. And then the lower one is 2, 1.1 to the 15th times 1. This is actually 0, so that's just the only thing is that. So that's how many rabbits and foxes there will be. 15 generations down. So, and it's a lot easier, right, than doing, did anyone try multiplying this by itself 15 times, just for fun? You know, you're really bored, boring lecture, Brother Corey. Yeah, it's like, put me out of my misery. I'll just sit and do that so I don't have to listen to him drone on. Okay. So, Peter, so that was your question, was like, how does that actually work? This was an example. Does that make sense? Okay. So other questions from what we've done today or anything from the reading? Okay, let's hit a few highlights from the reading. So we should have learned how to find the eigenvalues and eigenvectors of an n by n matrix, not just 2 by 2, because now we know how to find determinants of larger ones. We can find the eigenvalues and eigenvectors of the larger ones. We know what the characteristic polynomial and equation are. The eigenvalues of a triangular matrix are the entries of its main diagonal. We know one more addition to the invertible matrix theorem. If 0 is an eigenvalue, is not an eigenvalue for A, then it's invertible. So if 0 is an eigenvalue, then it's not invertible. If it's not an eigenvalue, then it is. Right? Because that means you have at least a one-dimensional eigenspace when you haven't changed the matrix. Right? You have a null space that's not just the 0 point, the 0 vector. You haven't changed it, and you still have a null space that's at least one dimension, so it must not be invertible. And the set of all eigenvalues of a matrix are linearly independent set. Oh, I skipped one. The strategy for finding higher powers of a matrix with a lot less computation. So that's what we did here. And what we're going to do in 4.4, we're going to build on this. And you might recognize, hey, you know what? Can't I write this as another matrix multiplication? So I have a 1/4, 1, 1, 0 matrix, and then have 2.5, a column vector. We're gonna use that notation in this. This will cut out a bunch of work for us in the next section. And here's the big thing for geometric and algebraic multiplicity. As long as the geometric multiplicity is the same as the algebraic multiplicity for all of your eigenvalues, you can do this. You can do this strategy and make the computation easy. But if the geometric multiplicity is different than the algebraic multiplicity of even just one, then you're toast. You can't do this strategy. Yeah. So, okay, better stop there. Have a great one.